Hello A-level chemists, welcome to Required Practical 8 where we're making cells, and this is for the AQA specification, but remember this is applicable to all exam boards because you have to do electrochemistry in all of your exam boards. So let's have a look at the question. The standard hydrogen electrode is used to determine the standard electrode potential of other substances. Correct. We've got to state the conditions and substances needed in a standard hydrogen electrode, SHE. Okay, cool. So 3 marks for this. So we need H2 gas in a standard hydrogen electrode, and we need a pressure of 100 kilopascals. You can't say 1 atmosphere, but you are allowed 1 bar. I believe the definition changed in 1982. So what else do we need? We need an acid, so you could pick monoprotic acid, something like HCl or nitric acid. That's AQ, and 1 mole per decimeter cubed. If you pick H2SO4, which is diprotic, then the concentration is to be 1/2 of 1, which is 0.5 moles per decimeter cubed. The reason is because when that dissociates, if you've got 0.5 moles per decimeter cubed, the concentration of the protons is going to be double that, so it's going to be 1 mole per decimeter cubed. So it's good to know what it's going to be for diprotic acid. So that's going to be 0.5 moles per decimeter cubed. So we've taken into account the gas that we're using, the acid that we're using, but remember we need a solid surface for the electrons to accumulate on and a catalyst, so we're going to use a platinum electrode. So we need a platinum electrode and we need a temperature of 298 Kelvin, nothing else. So that's where your marks are coming. So 1, 2, and then a 3rd mark here. Okay, let's have a look at a follow-up question. I think it's a cracking question. Okay, so there is a lot of writing here. I'm not going to deny that. There's a lot of writing, and it's a whopping 6 marks with no scaffolding really. So just here is the question, go. So let's try and dissect and decode the question. So it can be challenging to maintain consistency when setting up a standard hydrogen electrode. So as an alternative, we can use a copper 2 plus copper electrode as a secondary standard because we know what the reduction potential is for the copper half cell. So a student does an experiment to determine the standard electrode potential, i.e. the reduction potential for this electrode. And when I'm reading that, I'm thinking, okay, I don't know what the half cell is, but I could probably work it out. So I've got this TO2 plus. So the titanium, let's work out the oxidation number. So oxide is -2. So therefore the whole species has a +2 charge. So my titanium must be in the +4 oxidation state. Okay. And then it's going to titanium. So I want it as the reduction potential. So the titanium has 0 charge. So this is a 4 electron reduction. And if I keep on reading, it's under acidic conditions because we're dissolving it in sulfuric acid. Okay, that helps me because I can balance the oxygens on the left hand side with 1 water molecule, so that takes care of my oxygens. And then if I balance the left hand side with some H+, there we go. There is my half cell. Okay, and then it tells me, if I keep on reading, we need to demonstrate that the reduction potential for this half cell is -0.88 volts. So we need to show that effectively. Okay, so what do we do? So I'm going to go back to the blurb at the beginning. So to prepare this, we need a solution of these ions, and we use titanium oxysulfate, TiOSO4, and we dissolve it in sulfuric acid to make 50 centimeters cubed of the solution. Okay, so this is where the standard conditions really come in handy, okay? So I need some mass of my TiOSO4 that I'm going to dissolve in some volume of sulfuric acid. And I know the volume, it's going to be dissolved in some sulfuric acid first. So here's some sulfuric acid, so we'll dissolve it, so we'll add it into here. And then what we're going to do is we're going to make it up to the mark in a volumetric flask. And that's 50 centimeters cubed. Okay. So when I'm reading this, I know that that solution needs to have a concentration of 1 mole per decimeter cubed. So then what am I thinking? So if I know the concentration that it needs to be, I'm going to go to N equals CV, and I'm going to partly do the question as I'm going along, okay? So I know that N equals C times V. So if I set the concentration to equal 1 mole per decimeter cubed, because that's what it should be, and I know the volume is 50 centimeters cubed, then I can determine the number of moles of my titanium compound that I need. Okay, so the concentration is 1 and the volume is 50 over 1,000. So my number of moles is going to be 0.05. Okay, so that's the number of moles of the titanium compound that I need. Okay, so there should be 0.05 moles in here, and all of those 0.05 moles came from my solid that I started with. So then, I don't know what mass I need yet, but I've got the number of moles, and I'm given the MR of my titanium oxysulfate, which is good because then, to work out the mass needed, I'm just going to multiply the number of moles, which is 0.05, by the MR, which is 159.9, to get the mass. So let's see what we get. So we should get a mass of 7.995 grams. Okay, so 7.995 grams gives me a concentration of 1 mole per decimeter cubed. Hurrah, because that's standard conditions. Great. So definitely setting up the scene of how I'm going to answer the question as well. Okay, so what else do I have? I've got a copper 2+ copper electrode setup. I've taken care of that point. So I've got some sulfuric acid. Great. I've got a strip of titanium as well. And then we've discussed how I'd prepare the TiO 2+ solution. And then let's think about how I'm going to set this up. Okay, cool. Let's go. So then when I'm making the cell, which electrode is going to be on which side? Now I could think, I mean, you'd get marks for either way that you set it up. Your value just has to be consistent, okay? Your value just has to be consistent. So what I'm thinking, if the titanium half cell is more negative, then it should go on the left-hand side. So we're saying that is the species who is oxidized. So I need a beaker, and I need my electrode in it as well. Okay, and we can use this image. It's worth drawing it out, I think, and just annotate your drawing, show the examiner you know what you're talking about. Okay, and then what I'm going to do is I'm going to connect these guys up through a salt bridge. And then I also need to connect them up to a high resistance voltmeter. Right, let's do that again. So I'm going to go straight up. Sorted. Okay, and then we're going to put a voltmeter in. Done. Okay, great. So then the only thing missing from my beakers is the solutions. Obviously there aren't waves here, but I'm going to put some ripples just to show that it's a solution. Okay. Excellent. So let's start annotating this guy. So I've got a high resistance voltmeter there. So let's just put the titanium as the left-hand electrode. So there's my solid titanium strip. So I'm going to have a solution of TiO2 plus 1 mole per decimeter cubed. And on the previous slide, I showed how I got that, okay? So here is my salt bridge. And then on the right-hand electrode, I'm going to have a piece of copper metal and copper 2 plus, probably from copper sulfate, and I've got 1 mole per decimeter cube of that as well. Okay, so now let's think about what the E cell value is going to be. So then E cell in the current configuration, we'll do it the normal way. I'm going to say is E red minus E ox. So the left hand side by definition is being oxidized, and this side is being reduced. So E red, if I'm not mistaken, is plus 0.34 volts minus 0.88 volts. I believe these are the values. So then let's see what we get. If we process this, E cell works out as something positive, so it should come out as what, 1.22 volts. Let me just double check that. Yep, and it does. So therefore the electrode potential for TiO2 plus 4 electrons plus 2H plus going to titanium plus H2O is minus 0.88 in that direction. But remember what we're doing. So what we're really doing is we've got this titanium, we're oxidizing it, so we're making it go in the opposite direction. So if we're oxidizing that, that value can be flipped, and the copper goes in the direction as we expect, so the copper 2 plus is reduced. And that's plus 0.34 volts. Okay, so then looking at this question, where are the marks coming from? So I guess we're getting a mark here for stating the mass of titanium oxysulfate that we need. Then we're dissolving in sulfuric acid and making up to the mark in volumetric flasks. That's the first bit, okay? And then what are we doing in the second bit? So we need a piece of titanium dipped in 1 mole per decimeter cubed of TiO2 plus solution. And then we're connecting the solutions with a salt bridge, and we're showing that. Also connecting through a high resistance voltmeter. So high resistance voltmeter, we want to limit the current flow. Okay, and we've got a copper electrode on the other side, okay? So then we work out E cell from E red minus E ox. So this is going to be E copper minus E of the titanium half cell. So then we get an E cell value of plus 1.22. Sorted. I guess if we have copper on the left-hand side, if copper is on the left-hand side and titanium is on the right-hand side, we're going to get the same value, but it's a different sign. So it's going to be minus 1.22. Okay, really good question. Really shows your understanding of half cells. Okay, thanks for watching. I hope that was helpful, and we will leave it there. Ta-ta.